Okay, so good afternoon, everyone. Uh, I think last part is here, right? Uh, so just a quick review on the log and just a summary. So if you have the ln with absolute value of x, if that is your function, then we could imagine that it has two different intervals. You have the ln x and ln negative x. And why this is important is you will see that when we derive these two piecewise functions, it's getting the same conclusion, which is 1 over. It's always happening here. Okay. Okay. So it's going to be the same conclusion, which is 1 over x. And then we can also prove the statement by taking our graph. Okay. So this is the graph. So the blue curve is the ln, absolute value, the absolute value of x. So ln x will be on the right side, and ln x will be on the ln negative x will be on the left side. So if we take sometimes to check the slope, if you check the slope here, which this is going to be all positive slope, right? But see that from this becoming a little bit near horizontal, right? It's getting more and more going to be horizontal, which means that the value itself is decreasing. The slope value decreasing, but still all positive, right? Positive means on the top, right? In this area, right? So it starts from here, it's decreasing. The same way when we see the slope is going nearby the horizontal, which is decreasing. Okay? Decreasing means not negative, but the value is decreasing. Okay? The left part, we see this is all negative slope, and then you will see also from this, let's say this is horizontal here, and it's getting negative, which means the value also decreasing, which means that this is correct. It's in the negative region, but this is also decreasing. And then by some observations without checking the exact value, we know that this is going to be roughly they are true. Roughly visually they are true. Okay. So this will be the blue one will be the ln. The red one is the 1 over x. Okay. So that is important. Okay. So the importance using the ln with absolute value is because when we derive both cases, they gave the same result. So later, if you want to take antiderivative or the integration of 1 over x, we need to make the statement the absolute value. Because it can be ln x or ln negative x. Okay, just a quick review last time. Okay, next is, I think, this one. Okay. So what will be the first derivative? And how to find it? Yes, logarithmic method. So if you have a function with power of functions, why this always happen? The cable is quite loose, so it's okay. So every time you have a function with another function, the best way to solve this is taking the power and make it going down. So how we are going to do that? We take each side taking log, taking ln, or log. But I think maybe easier to just using ln, log e. So take both sides. So let the y, and that's making. So take the ln, both sides. And then derive. And now using the implicit. Okay. ln y becomes 1 over y. And then don't forget dy dx. And this will be, this is f, this is g. We have a product rule, right? So we have ln x and then dy dx equal, dy is our original function, right? So we have written again. And I think you can just stop until there. Then that's the derivative. If you want to simplify and then maybe you want to combine these two on 1, 0, it's okay. But I'm just stop up until the answer is okay. And the left part here, I think I can put it here. This is how it looks like visually. So we say this is the blue one is the F. Okay. And then you will see that at this point here, exactly at this point, this is when the slope are 0, okay? Which are in the f derivative, it's crossing this, right? Okay. So the way we observe our functions, if we want to know how the derivative will looks like, is first we check whether we have the slope equals 0. If we have slope equals 0, then we can pinpoint, we can maybe mark the axis. Okay, this is, we expect the curve to cross the x-axis. Okay. So that's how we see the slope equals 0. And then we can determine which one are negative, which one are positive. Like for example, this one is negative, it's going down, but then it's going down, but it's going to be increasing in value up until 0, which means it's increasing, but it started from the negative region. Okay. Up until we crossing this 0. Okay. And then after we get 0, what happens? We are going to increase. So we are going to have positive, 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 and then increasing in value as well. Okay. So it's positive slope, but it's also increasing in value, which means the red color here are our derivative. Okay. Okay. Any question about this part? Do you want? Are you still confusing about how to derive this?
Can you do that again, the derivation for that? Just do for that.
Which one?
Just do the derivation again, sir.
This one?
Yeah.
From this one?
Yeah.
Okay, the first thing, okay, let me show you the steps. This is y equal x to the power of square root of x. We take ln, okay. We move the hour down here, okay. We take the derivative for all the components. ln y becomes 1 over y divided by x, okay. This one, product rule. F prime becomes 1 over 2 square root of x, and then g. This one is g prime, ln x 1 over x. and multiply with f. Get it? Okay. So this will be f prime g, g prime f. Perhaps next week will be quiz. And now you are wake up. I'm happy. Quiz will be chapter 3. Only the techniques, okay? Like from the product rule, quotient rule, and the combination of that, the chain rule, until implicit and log.
Just to differentiate.
Yes, just to differentiate function. Yeah, only the techniques. Only the techniques.
Is this chapter 3 or chapter
3. Is it 3?
And the quiz next week is chapter
3.
3. So do we not have a quiz for chapter 3?
I think you already have. You already have
Oh, the first one is what?
1, 2, but not all 2, but like
Yeah, I
part
do
of.
not remember already.
Yeah. Yeah, no, he's actually yeah, chapter 3, quiz next week. Okay, next Thursday. Okay, Thursday, not Tuesday. Next week, but Thursday. Okay. Congratulations, students who just come. Next week we have a quiz.
Yes, sir.
Yes, again. You can check some practice. I put in the middle, the first part. I will send you later another one for practice. This way. The practice. There's Thursday, next week, but not this week, next week. Quiz will be 1 hour, okay, 1 hour only. So 1 hour in class and 1 hour in class. Today or? Yeah. And today we will have 3-hour class, okay? No TA. This week, no TA. Okay. So today will be 3-hour class. I hope you don't mind. Okay. But perhaps your TA will give you homework, okay? Okay, now to start some practice, start from this. Find the derivative. Find the derivative.
Actually, there was something like about something that like I
Banyak pertanyaan saya.
Jangan dede.
Sebentar. Midterm check apa tuh? Kan minggu depan kan quiz. Minggu depan lagi midterm. Ada apa tuh? Midterm saya 1 sampai 4. Apa 1 sampai 3?
Saya mau sampai sampai 4.
Oh, 1 sampai 4. Habis itu ada kayak define limits with yang alpha and something.
Kayaknya
Ya, sebutkan tuh
supplementary.
supplementary kan oke. Jadi sama kemarin setelah ini apa ya? Kemarin kan habis itu apa? Saya lupa soalnya.
Iya, baru sampai sini. Ini kan sebelumnya.
Ya ini sebenarnya pas cuma penjelasan lah pas akhir-akhir.
Iya, ini kan buat menjelaskan yang masih.
Ya soal terus kan kemarin minggu lalu saya pas akhir kajiannya kayak gitu.
Oh iya.
Sangat itu sendiri kan?
Nggak apa-apa.
Ya.
Okay, so I think you can think in 2 ways now, or maybe several ways if you would like. So first one is just original chain rule, just take derivative. Like for example, we take this as 1 over 2. And we differentiate and this will be 1 plus. You can simplify, but I am lazy now, so I will just end up to there. Okay. So we can do this, or we now have the implicit and also logarithmic. So we can add log and then we can do implicit. So we can write this as y and we can write y squared, and then we take implicitly. This will be 2y dy over dx equal 1 plus, and then this will be 1 over 2y 1 plus, or this will be 1 plus 2. Same, right? Same. Okay. So now you can have several options. Whenever you want to derive something, there is no like exact one solution. You can have several routes. Okay. Depends on your preference, which one you prefer. You can get the algebra first and then derive, or you can directly derive. For example, this part, I'm taking this into implicit using the squared and then just implicit. You can also take the ln. Okay, I take this squared both sides, or you can take the ln, which give you the idea of, so ln and then it's give you the ln y equal half ln, and then taking the first derivative, and then this will be 1 over y dy over dx, and then half, and the whole thing here becomes 1 over x plus square root of x, and then you multiply with 1 plus, so dy dx is y is what? X. This is x plus and we have this. We can take sometimes to cancel this 2. We can cancel this 2, right? And we can write the same thing with the previous one. This is the maybe better if I write some notes here that the square root multiply with this is equal. So we can cancel this 2, keeping this as a left over. So the same results, okay. So you can like pick which one do you like. Sometimes one solution maybe you think maybe it will be faster than the other one, or maybe you could understand more than the other solution. That's okay. Which one you prefer, that is up to you. I think it's up to you. So in exam, all the roots they are correct. Okay, now I would like to modify the questions. Okay? I would like to modify and make it a little bit weird at the glance. So let me write the question. Okay, let me write the question here. The question seems a little bit weird. It's a little bit weird, but take your time, think clearly, and find the first recipe. I forgot where I get this question, but it's maybe someone using it in like a math Olympiad. I think long time ago. So this type of question, like the one that usually shows up when you take some like national test or even the Olympiads. This is not like a regular question. The previous one that we did before, that is regular question. We have like expectation of the functions, and then we have the solution directly. But this type of question, we need to think how to solve it in a simple way, but still it is reasonable to solve. Previously I mentioned like I have several ways, right? I have several ways to solve it. Think from 3 methods that I showed you before. If you get the idea and then try using that idea, I think you will be successful in the future. At least for the mathematics part. Good. One student solved it. But I think it's make it complicated, right? So I think you can skip that. Okay, but it's this one of the options. What's constant? What and what?
Because like it keeps going.
Yeah. Let's keep going. Not a constant, but maybe another variable. You decide. you get an idea? Okay, so we define this as y. Okay? And then the question is, this doesn't specify like how long this is going to be. Like they say like maybe it's going forever. That means if we just look the second part, the square root here, we can think this as y, right? Did you get my point?
Yes.
Yeah. You get it, right? Okay. Did you get it? No? So if this is y, and if we just look at this one here, this second square root inside, this is also is x plus y, right? So somehow you could make it into square root of x plus y. Okay. So we can somehow, through this information, we can see that this is actually the same y. Okay, so I think let me erase this part. And then we get right just like that. Okay, and then we can take squared both sides. Okay, and then let's just derive it. So this will be 2y dy dx, and then equal 1 plus dy dx. We can solve for dy dx. So dy dx, and then we can move to the left side, we come to y minus 1. Okay, and then this equal 1. So dy dx is 1 over 2y minus 1. Or we put back our y again. This will be 1 over 2, and then put everything. Minus 1. So actually, our implicit differentiation can be helpful for this type of questions. Okay. This is when I first tried to solve this, it's also like because I feel it's weird, but then I realized that it's getting repetitions. Okay, now we go to the next part in our course. So the first part is just a summary and a recap. So this is y prime. Okay, any question about this one? I hope not too many, because this is actually a tricky question. Not really like a course that, like a question that mostly going to be asked in regular exam. Okay, now we move to here. So let me put this around here first. So we know that if we have f of x, if we have this ln, the first derivative will be 1 over x, okay? And then the value of that 1 over x when x equal 1 is also 1, okay? So within this number, we can write our limit definition, or maybe let me write the original one. Okay, let me write the original one is okay. So if we have x equal 1, it means that this is going to be limit. I forgot the limit. So limit 1 plus h minus f1. Oh, why this is 1? This is x. Sorry. And then divide by h. Now if we change the h to x, divided by x. Okay, we change all h to x. Then we using the function ln. Now we have the right. Limit of 1 over x, and then multiply with ln, or maybe let me write ln 1 plus x. Okay. And we can write this in terms of, so we can move the 1 over x to here. Okay. So we have now this expression. But then we know that by our derivative, when x equal 1, the derivative is 1, right? So this thing is actually equal to 1, okay? So we can exchange the ln by taking e, okay? So we can take the e like that. It means that e with power of this limit, okay? Or we can write limit and then e with power of ln 1 plus x 1 over x. This is equal to e. And then this will be cancelled, right? So the limit, I think let me put this down first. So this limit of 1 plus x with power 1 over x, this is actually equal to e. And this will be the definition for the e. Okay. So we can approach the number e by taking this function, and then observe when x approaching 0. When we approach x to 0, when we observe the function, the number or the value will approach E. So this is from the fact that we can have our limit definition, okay, or limit definition. We know that when we derive ln, it becomes 1 over x. And at x equal 1, the value is 1, which is this. And then we take the e as the exponent, and then with this as a power, so we take that in both sides. Or do you understand how to do this? Not good? So I think you will know in more details maybe later in basic. And then we have the e, oh, it's going to be e. And e with power of ln, that will be cancelled. And basically we say that it's cancelled because this is ln is log e. Okay? You have base, and you have log with that base. Basically, you are cancelling the log and the e. So, in other words, if n is 1 over x, so if we take n going to be increasing largely, then x will approach 0 from the right side. Then we can also rewrite the e with n, and this will be 1 over n, and this will be n. Okay, another way to represent the e, okay, from the same sources, okay, from the same approach. Then of course we can take this approach into our table, check the values, and then check the functions. Like from these two tables here, so this is the functions. And this is some value. So the more we are getting closer to 0, so making smaller, we get more or less getting closer to the e. Of course, I think no one knows how many decimals e have until now. No one knows. And maybe for several years, maybe some scientists found, oh, we found another decimal, I'm not sure how much decimals we have found. And that is one research in math, to find the decimals behind the. Let's see. So yeah, that's it, the logarithmic functions. Okay. We have another topics aside from the logarithmic. It's the inverse trigonometry. The inverse trigonometry, which perhaps also in your quiz. Okay. Okay, any question from this one? This one is just this definition. This is the definition for E, actually. Definition for E. We conclude that this is the definition for E using the limit. This is coming from the fact that we know the ln, we know its derivative, and we can also relate this to our first definition of derivative, which is using limit. Using limit, fx plus h minus f of x divided by h. Yeah. Yeah, it's a little bit weird, but this is just to show you that we can represent E with another form. So the E can be represented as a series, E can be represented as a, like intuitively finding the numbers between 2 and 3, and then we can have some sort of the same, or we can conclude that there will be some number which can make it equal 1 when we take the logarithm or exponent. Okay, so next part is the derivative of inverse trigonometry. So what is the inverse trigonometry? So we will have at least 3. So sine inverse x. This is inverse, okay? It's not 1 over sine, okay? It's not 1 over sine. Every year, I was told like several times in class, but in the exam, there's maybe 1 or 2 students that write this is 1 over sine x. Okay? So I need to mention this, okay, so that I know I have told you. And then we have cosine, and we have the tangent inverse. So what inverse means? Inverse means that we are interchange domain and range, right? So if we have this, then we could rewrite in terms of x that this will be x equals sine y, okay? So we can rewrite that. So we can rewrite this as x so this is x. Same way this is tangent y. So the value of y, if you imagine the sine, cosine, tangent with some numbers, with some value, this y is the angle. Okay? Is the angle. Okay. I think this is not in your textbook, but I need to mention this. This is much easier to be understood. That the y is an angle. So what does that mean, and how we can make it into our understanding? So remember that the first thing we have, if we want to have an inverse, so remember that inverse or the F inverse like that, the first thing is requirement need to be 1-to-1 function, right? So 1-to-1 function means when you have a graph and you are taking the horizontal line, it's only crossing one time. If more than one, then it's not 1-to-1. So what is our graph in trigonometry? Let's start from sine. Our sine is going to be at least like that, right? And of course, in the horizontal line, we have crossing these 2 points here, which means it's not 1-to-1, okay? But then we need to make sure that this can be applicable in our inverse, okay? That this trigonometry can be applicable. So one way to do it is we are going to restrict some domain, okay? So we are going to restrict to this domain here, okay? So we are going to restrict that the domain will be or in our case, the angle here need to be at least from this interval, okay? From -π/2 until π/2. So by limiting the angle, we are going to have 1-to-1 function. That's why we have the inverse of sine. Okay. If we do not take these restrictions, then we are not having any 1-to-1 function. But later, if you see any inverse of trigonometry, that means we assume that it is one-to-one. We have restricted the domain, okay? Because the question may be not always saying, okay, we need to restrict the domain, blah, blah, blah. So we need to have like a definition first that it needs to be, need to be restricted in the domain. Okay. So by taking this angle, we can easily imagine a triangle. A right triangle. Okay. And then let's take the angle here as our y. Okay? Let's take that as our y. So take this y. Okay. So x is equal sine y. Sine is from here, position, divided by this hypotenuse, right? So this x, it means that it will be x. It will be 1. Okay, and this will be square root. We're continuing that triangle. Okay, we go back. We go back to the reality. Okay, we go back to this triangle, and then this is triangle for the x equals sine y. Okay, so I'm going to write here that this is for x equals sine y. Okay. Y is the sine inverse, right? Y is sine inverse. Right here. So y is sine inverse x. Our goal to derive the sine inverse. So we need to make the y becomes dy dx or becoming dy prime. Okay? And we need to figure out what will be. Okay. So to derive this, we can think from this perspective, okay? From the x equals sine y. So take the derivative for this, okay? For this implicitly. So we take implicit differentiations. So take derivative. So x become 1, right? And sine becomes cosine, right? And don't forget that we need to take dy dx for every implicit differentiations. So dy dx, the same dy dx that are being asked for our sine inverse. So dy dx become 1 over cosine, okay? Okay, not yet finished because it's still on y. Y is this. Cosine y is this one, the adjacent, divided by 1, right? Okay. So this is going to be, let me write here, d dx of the sine inverse x is equal 1 over square root 1 minus x squared. So that's how we get the result. My suggestions, not to memorize this, but it's good if you memorize. But I think if you keep on the triangle, every time you change the question, you see a different question but the same inverse trigonometry, you can try the triangle. It can be tangent, it can be cosine. As long as you can define the triangle, you can solve every inverse trigonometry problem. Okay? I hope it's helpful. It doesn't mention any triangle in the textbook, it's directly derived. But I think it's really helpful if you can imagine the triangle.
you scroll up a bit, to take a picture of the triangle?
The triangle here, right?
Yeah.
Okay, he's always optimistic. Not sure if you understand what that. You can find it in my sticker. I wrote it. So for every inverse of trigonometry, like sine inverse, cosine inverse, and tangent inverse, they are all having different triangle, different definition of triangle. Okay? So as long as you can define correctly and you can implicitly differentiate all the inverse within these terms, implicitly derived, you will solve all the problems in the inverse trigonometry. It seems so simple, but it's actually really, really helpful. Which one? This one? Okay, so cosine y, we define y in our triangle. Yeah, cosine is this side over 1, right? Okay. So let's try another function, okay? Still in the inverse. So let's try tangent inverse. So how to start? So we can let this become y equal tangent inverse x, and then we can solve for x is equal tangent y, right? And what's happened is we take another triangle and then state y is here. So now we have the tangent. So where's x? Where's x? So you could think this x is like x over 1. So what is supposed to be the tangent? The side divided this. Or is it correct? Correct, right? Okay. So we can say that this is x, this is 1. So what will be this? Square root of 1 plus x squared. Okay. So this will be 1 x Now, what is the derivative of tangent? Have I explained derivative of tangent? Or do you know? Yeah, derivative of tangent. Okay, so tangent. I think the best way to explain the tangent is through the sine y. We derive this, and we take the quotient rule. So sine so this is f, this is g. So this will be cosine squared y minus g prime is minus sine, so minus sine squared y, which is going to be 1 over cosine squared y. This is x. And this will be equal to secant squared y. So the derivative of the dy, secant squared y, okay? Now, let me put here. Let me write again x. Let me write here x equal tangent y. Now we are going to derive with respect to x. This will result 1. And tangent, we have the secant squared. So secant squared y. And then dy dx. So dy dx is secant squared become 1 over secant squared, or this is actually cosine squared, right? And look at our triangle. What is the cosine? 1 over the hypotenuse. But we squared, so that's why it becomes 1 over 1 plus x squared. Okay? So we take this tangent inverse of x. This will be 1 plus x squared. Okay. So we have now established some of the fundamental functions for the inverse of trigonometry. And this is some visuals on the function itself. So this is the tangent inverse. And this will be the derivative. So you will see that it's going up and then getting higher and higher. So it's going up and higher. This is positive, all positive region. Okay. It's all positive region, so it's going up. And at certain point, the value is declined, right? Decline, but still positive. So it's going to be declined like that, but still positive. This value here, this is what we call the, later we know that this will be the inflection point. That is when the second derivative is equal to 0. Okay. But I think we don't need to worry about that now. We need to worry later. Okay. So similar to what we have done before, like all the type of functions can be combined, and they all can be related with each other using chain rule. Okay, so the question can be expanded and makes more complications. You can try if you want, you can try by yourself the cosine inverse. It is similar with these two process. Take the triangle, okay, and then take some time to define all the components, and then derive implicitly, and then you get the result. Check the result with the triangle, and you need to rewrite in terms of the variable. Okay. For example, a quick example, if we have like x tangent inverse square root of x, like that. So we can see that this will be tangent inverse x, the f prime, tangent inverse square root of x plus x, and then multiply with this. Let me write one by one like that. And then this will be 1 over 1 plus square root of x but squared, so it will be x, and then multiply with 1 over 2 square root of x. So we have tangent inverse x, square root of x, plus square root of x divided by 2, 1 plus x. This is cancelling and giving you square root of x. But sometimes, maybe in the middle of process, like for example this part here, you are getting stuck because you forget how to do the tangent inverse. So the best way to solve this is taking this tangent inverse and take some time to check the triangle. Check the triangle. Maybe in another note, you write this and you get the conclusion, and then you write with conclusion and write using this solution. So I believe in some way you are not always remember. Like I always forget for cosine inverse and sine inverse. I always forget that, so I always going back to the triangle. Okay. I forget like if this is 1 minus x squared or x squared minus 1, I always forget that part. So you can go back, take some time to draw the triangle, and then define the components. The more you do that, the more familiar you are with the functions, and I think that's the best way to make it familiarized within yourself. Okay, any questions so far? Okay, maybe several examples to let you practice. Oh, maybe the conclusion first. Conclusion. Let me write conclusion here. So this is some inverse trigonometric functions that you can derive from sine inverse, cosine, tangent, and then cosecant, secant, and cotangent. I think the easy one to memorize or remember is the tangent inverse. I think I always remember this, and I'm not sure why. But for cosine and sine inverse, I always forget how it looks like. And even I don't remember this. I don't remember this. But if you want to memorize, good for you. I don't want to make my head full. Okay. But the concept, triangle. The triangle. Okay, what if example, what if we have y cosine inverse, but then we have sine inverse inside that? So what it will be the first derivative? Is it worth it to be an exam? Is it worth it to be in the exam or not? Okay, you can try. Okay. So first, you need to establish the cosine inverse, or you can use the table. I think if you ever pass the table, you can directly write the solution. I put the table up there so you can directly run. You mean like what? Can you write something? I think different case. So if you follow the table, then you can derive the cosine inverse. Using the x squared is this sine inverse, and then multiply with the chain rule of this, which is this sine inverse, which is the first one. Okay. So based on the table, because we have now the table, so it will be -1 over square root of 1 minus sine inverse x squared, and then let me write one by one. This will be sine inverse x like that. So we have the first derivative is, this will be, let me just write again, 1 minus sine inverse x squared multiply with the 1 over okay, I think we just stop until here. Still okay. I don't think if we like simplify will be necessary, and that will not really meaningful, so just stop here. Yeah. Okay, do you want more example? Let me check what kind of example we have. Another way, if we have, like for example, y equal ln, and then we have sine inverse of x squared. I think easy, right? Okay, so this is just taking down the inside function and then taking the chain rule of the sine inverse, which gives you and the sine inverse is 1 over what? 1 over square root 1 minus the x squared, but it's squared, and then we multiply the chain rule with 2x. Or if we want to write in the big fractions, okay, I think more example I will provide later on, and I will select interesting question. This is regular question. Interesting means it's actually not difficult, but you need to think. Okay, so finish the inverse trigonometry. The next part, still in chapter 3, is related rate. Not included in your quiz, but perhaps in your final, or maybe middle exam.
What is the midterm?
Oh yeah, midterm. Good point. Let me check the Let me check the schedule. Okay. So I think based on what we have. Oh, and also we have a class on Saturday. I think I mentioned that last week, or maybe last week. Yeah. Yeah, and then I remember, oh, we have a class Saturday. So we have Thursday, Saturday, Tuesday, Thursday, Tuesday. I think maybe our midterm in November. Okay, it can be November 2nd or 7th. Okay. This, if it is in 7, since usually you have a TA class after 1 hour, right? I can rearrange the TA class at the beginning and then our midterm. Okay. If that is the case. If not, then 2nd of November, or if it is going to be delayed much, then maybe 9. But I'm trying to finish this all the chapter 3 and also getting into chapter 4. This one? Sin y. Define sin y from here.
And then that's it.
Yeah, sin y is 1. But this I think not correct graph. We need to define graph with this one.
Oh, it's a different
Triangle.
triangle.
Yeah. For each one of them, different triangle.
Huh?
Yes,
Oh.
different triangle. Okay, let's go to the next section, which is the related rates. Okay. So there is an example here. So you can read the example. So air is being pumped into a spherical balloon, and the volume increase, and we have a rate. Okay. And then it's asking how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So this type of question, okay, this is what we call the related rates. Okay, so this is what we call the related rates. So related rates mean you will have some like phenomena that related to rates, some change in either maybe velocity or maybe some other example. Like for example, this one, it has a balloon and it's getting expansion. It's getting expanded, the volume increase. Of course, when we increase the balloon, the volume of the balloon, it also has the rate, right? It can be the rate of the volume itself. It can be the rate of the diameter or the radius. So we are going to define all that and then try to find the connection to solve this problem. It is a typical problem in what we call the related rates. So first, we need to understand what's going on here. If we must draw, then draw. If it makes more simplified. Like for example, the balloon, maybe we throw the balloon like that. And then in some cases for the related rate, we need to know assumption for some geometry. For example, balloon. What is the volume of balloon? Anyone remember?
4 PR3.
Yes. Okay. So we need to take the example of the volume of the balloon. Okay. So volume of balloon, or maybe let me write sphere. Okay, more general. Is 4/3 pi r cubed. Okay. So imagine that maybe we start from this small balloon here, and then maybe another assumption, it will be increasing homogeneously, because we are not really making these complications, right? So maybe the after it's increasing, maybe it becomes this green one. And this will be having the R, okay? And we know that the volume increase at this rate, 100 centimeter cubic per second. So what does this mean? This is the rate of the volume, or we can write the terms is dV dt. Okay, this is 100 centimeter cube per second. So every second, it will increase 100 centimeter cube. Okay. Now, how do we relate the radius? The radius you can get from this formula, this r cubed. Now we already have all the necessary tools to derive, right? To derive. We have a variable, so we let this r as our variable. Okay. And v also are variables. So v we take derivative with respect to t, because we want to make sure that this is the rate. So we write this will be dv dt equal for pi is a constant, so we just write pi, and then 3 will be cancelled because of the r cubed becomes 3r squared. So we write this will be pi r squared, and since r is also another variable, but we are going to derive with respect to t, we are doing it implicitly, so we write the r dt. Okay. The same principle when you derive the y before. Okay. So now you have the rate of your radius. It's asking how fast is the radius increasing, which means this is the one that we are going to find. We are going to get. So the balloon increasing when the diameter is 50 centimeters, or when the radius is 25. Okay, so we just plug into the equations. So we know that the radius is 25. So at r equal 25, so the r dt is become, dv dt is 100. So 100 divided by 4 is 25. 25 divided by pi r squared. So at r 25, this will be 25 by 25 squared. So we can cancel. So 1 over 25 pi. Okay. No need to calculate. Okay. No, not necessary. And do not force yourself to calculate pi 3.14 and then you're wasting your time. Just stop there. So this is one example. So I will go through some examples and then we can see what is the general idea. It can be, it has like many variations. But usually how we solve this problem is we need to simplify the problem. So if you think like maybe there's another conditions, forget about that. Just make it simple, make some simple assumptions, and then try to relate to all the rates. Okay? Relate all the rates. It can be like geometric, like volume. It can be maybe you have like a car, and then it's getting meet up at some point with some time, and then how fast the car will move to that point, blah blah blah, and something like that. But usually you are going to define the maps. Maybe the map will define with a simple geometric like triangle, or even maybe other geometric as well. But that is the case. Or the second example, okay, it is about the ladder. This is pretty general example on trigonometry. So you have a ladder, like you put in the wall, and somehow maybe it's quite slippery. It's going down, the ladder going down, and how fast the ladder will going down. And if you put the ladder here, you will get the triangle, right? You get the triangle. So you can also have something like that. It's kind of like if you are not understanding what you are going to do, you will feel lost. Okay? You will feel lost if you don't understand. Okay? But if you know already the general idea, how this relates to the solution, you will know like, for example, this one here, you have a ladder. I have this at these feet. I think in your textbook should be in the metric system. But let's say we just consider the number. Okay, so this is 10 feet long. It rests against a vertical wall, which means maybe we put the ladder, maybe put here, okay, and then it slides away from the wall. Okay, the bottom of the ladder, which means let's just draw. Let's draw. let's say this is the wall. And this is the ladder. This is the side view, okay? Side view. So it says that the bottom of the ladder slides away from the wall. So it slides away going over there. So when this is going away over here, this going down, right? Okay. And then the ladder has a constant 10, okay? The length. It's asking, so if the bottom, we know the rate, so we know the rate of the bottom. It's asking how fast is the top of the ladder sliding down. When the bottom is 6 feet from the wall, so when this is 6. Okay. Sometimes, student, because he know, oh, this is 6. Oh, I have 10, 6, oh, I have this, should be 8. And then what, right? The question is not about that. The question is asking the rate, which means you need to develop some formula that can relate everything. And you see that this is a triangle. So I think Pythagorean can be helpful. This squared equal this, or plus this squared equal this squared. We can use that as a first step. But we still don't know what is this, right? So we name it. You can name it with any variable you want. We can name it A, B, maybe X, Y more makes sense. So Y and X. Okay. So let's name as Y and X. So this means that this is going to be dx dt, which is 4 feet per second. And this will be dy dt. dy dt is the one that we want to find. Okay. This is the one that we want to find. So our goal, let me write our goal. So we can write first that the connection between all of these variables are x squared plus y squared equal 100. Okay, that's for sure, right? So if we take derivative with respect t, it means that we are going to have 2x dx dt plus 2y dy dt, and then 100 becomes just 0. So we can have a short connection between x and y. Okay? So we have dy dt is equal negative 2x dx dt. Dy dt is negative x over y dx dt. This is our connection. Okay, this is the connections. Now, the question is also informed that we need to know the dy dt when it is 6 feet at the bottom. So when x equals 6, so we can write in another page, we can write when x equals 6, then maybe we can write like that. This is 10, 6, y. So y equal 8, okay, from the Pythagorean. So dy dt, then it is going to be minus x is 6, y is 8, and dx dt is 4, which gives you 3 feet per second. So this negative, do you know why this is negative? Hmm? Yes, you can think like that. Because if we think through this part here, if we imagine x is going to getting some additional length, y is getting decreasing. Okay? So when this is plus, this is going to be minus. But interestingly, in a weird way, if we want to make this as a negative and this positive, that can also be done. As long as we stay consistent and then the conclusion is still the same. You will find like some question you can think like both ways, but at the end of the day, if you are consistent with your definition at the beginning, you will have the same conclusion at the end. So plus negative and in the result is not really that necessarily important as long as you have good definition at the beginning. You can write the conclusion like, oh, it's going to be, the rate is going to be 3 feet per second, and then it's okay, it's correct. If you want to write negative 3 feet per second, okay, it's also correct. Okay. Depends on your definition. Okay. So this is a little bit complicated if you are not really careful in the understanding the questions.
Will this be the quiz?
No. But we'll be in the midterm. The quiz is not, there will be no related trace in quiz, but maybe in the midterm. But I'm trying my best because not everyone easily understand English, right? So perhaps I will help you to give you some clue, at least some diagram to be, so you can think easily from the diagram. The question can be varied. The same like ladder problem. Maybe it's asking the length of the ladder. Can be asking that. You can be asking this one, dx dt. What else? Yeah, I think that is 3 possible questions. Or maybe time. If you have like set some time and then you could compute how much the time will pass, and whether the ladder is going down or not. Yeah, maybe there's a more logic question. But I think no need to think too much. Okay, let me give you some steps here, as in your books. But I think it's too much words, so let me just explain. So read the problem, of course. If you don't read the problem, you don't know the questions, right? And then the second one, diagrams. Diagram is like this one. You draw the ladder. It help you to visualize the problem easily. And the name, give the name, give the notations, A, B, C, X, Y, or any variable, okay? And it's supposed to be function of time. So we introduce t. T is supposed to be the time, the rate. And then express the given information in terms of derivatives, which means that every time we have the rate of something, we write maybe dx dt, dy dt, dv dt, dA dt, or any dt. Okay. So express with t, dt, and then write the equation. Okay. Write the equation. So equation that relates all the quantities. Okay. It can be geometry or it can be any function that is described in the questions. So, but you need to write the equation, how to relate all of them. And use the chain rule and substitute. Substitute the given information and then solve for unknown rate. Okay, we have a break and we'll have another 1 hour. Okay. I hope you're okay with that. Okay, it's okay if you want to take a rest. Okay, 3 hours is crazy, right? Hello. Okay, welcome again to the class. It's supposed to be TA class, but it's me again. So let's go through another example in related rates, and then we may finish the class early. Is that okay? Yeah. So just for a few more examples, and then we can end the class. Okay. So another example is this. Okay. So read the question carefully, and I have this to help the example. So you see a water tank has the shape of an inverted circular cone. So inverted means we reverse the shape. So it's supposed to be the cone, but we are going to invert it. And it has the radius 2 and height 4. Okay. Water is being pumped into the tank. So you have the rate. Rate of the water, 2 meters cubes per minute. So we can imagine that the rate is actually the volume, okay? The volume of the water tank. Find the rate at which the water level is rising when the water is 3 meters deep. So of course, if the diagram is not given, the first thing you need to do is draw the diagram and then give name for all the variables that can be solved through the information. It can be the radius, it can be the height, okay? And I think there's 2 of variable that is important: the radius and height, right? So we can start. Imagine this is the water in the tank, in the water tank. So the blue color, the water, we have another R, which this is symbolized the variable, which means that it can be rising. It can be rising. So R, and then we have H, which is height. It's also a variable that can be also varied. So R and H are the variables. So the question is asking, or perhaps let's see this 2 meter cube per minute. This is so the water is coming to the cone, right? Which means that we can imagine the cone will change its volume. Okay, so we can see that this is the volume change, or the rate of volume change. And the question is asking, water level is rising, which means rising is this water level here, which can be determined from this H, from the height. So the height or the rate of the height will be, this is the H dt. This is the one that we are looking for. So it is asking dH over dt when the water is 3 meters deep. Okay. So imagine that this level is always changing, okay, and it's increasing, and we are going to find this dH dt when this h is equal 3. Okay? So if this is 4, maybe 3 is around here. So this is the one that we want to make as our value for our calculation. So the first step is we can relate all the terms within this shape with using this geometry. Okay? Volume. We can start from volume. What is volume of a cone? Yeah,
I
1/3. And then the circle, right? Pi r squared, right? And then pi r. So we can start to write the volume of cone 1/3 pi r squared, and then multiply with height. And then what's next? Imagine that this is V. Okay, so let me write one more. Right here, V 1/3. R is variable. H is variable. V also variable. It's always changing, right? It depends on R and H, and they are all variable. So if we derive directly with respect to T, we are going to have some difficulty on here, this R and H. Okay? So my suggestion, every time you derive with respect to T in this related phrase, we need to make sure that all the terms, they are all in the single component. If you see this variable beside like this, either we change R with H, or we change H in terms of R. And sometimes some information should be given in the question. For example, we have this triangle. We have this value 4, 2, H, R. We can have the ratio for the triangle, right? So from this one, we can have the triangle. So this is R, this is H, this is 2, this is 4. So R over H, we can say that this is 2/4. We can state H in terms of R or R in terms of H. Either way will be the same, but we want to make sure that we get this right, because this is our goal. So I think it's best to say, to change all into H, right? So then we can directly get dH dt. Okay, so change to R is half H. So change the equations. So we get, this will be 1/4 H cubed. Or maybe it's 1/12, right? So H cubed, this is 12. And then we can start. And now we are safe. We are safe to derive, okay? Because each side, they are all one variable. Okay? So we derive this with respect to T. I think I write too large, so let me make it smaller. So this will be dphi dt equal 3/12. It's 1/4. So 1/4 pi H squared and dH dt. And then we can start to plug all the numbers. dphi dt, we have 2 meter cubed. And H is 3. So we can take that. dH dt is, this is 100. Oh, why 100? 2. And then multiply by 4. Divide by 3 squared pi. It is 8/9 pi. The metric system is meter per minute. Yeah, I think most of the case it's either geometric, like a volume or area, or Pythagorean formula, or the trigonometric relations, like sine, some angle, and then you can have the diagram. Any question about this? Okay, right? Okay. Another question is this. Okay. You have 2 cars. Okay. You have 2 cars. Suppose car A and car B. So car A is traveling to the west. Car B is traveling north. And they have 2 different velocity, or you can see this one is 50 mi is miles per hour. But don't worry about metric here, because we don't really care much. Okay. That is for physics problem, for metrics. So both are headed for the intersection of the 2 roads. So you have the intersection, okay? And suppose that both car will meet. At what rate the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection. So you will not get any, maybe it will be difficult if you are not really visualize this in the system. So maybe we draw this. So we draw the car A traveling to the west. So let's say we are drawing the car A. Okay, I'm drawing like a elementary school students draw. So this is A, and then it's going on. Let me give some smoke there. Okay. So it's going over there. Okay. So let's say we have some intersection about here. So this is intersection. So the car B traveling north. So let's say the car B is going to be this way. Okay. So it's B. So this will be going north. So I think I will name the point on the intersection as C. Okay. And then naming the distance between A and C will be X. Okay. And this will be Y. Okay, again, the way we are going to solve this, we can imagine, like, for example, if you want to make this connected like a triangle, like for example that way, then we are going to define what will happen at our rate. Okay. So the rate is going to be to the left, right? And it seems that the x is going to be decreasing. The length is decreasing, right? I mean, the length for this x. And then this will also decreasing. Okay. So we could make visualization that this number can be negative. Or if you want to make positive, still okay. Okay. It will be. I will show you that both cases are okay. So suppose that we are going to connect this with some line over there, okay? And let's say this line is z, okay? So x, y, z. Okay? And we have the connection between this triangle using the Pythagorean formula. Okay, let's try to take this derivative with respect to t. This will get you to 2x dx dx dt plus 2y dy dt and 2z dz dt. We can cancel all 2. And then we can write that dz dt is 1 over z x dx dt plus y dy dt. Okay. So we are going to calculate when car A is 0.3 and car B is 0.4. Okay. So 0.4, 0.3 is Pythagorean. So it's supposed to be 0.5 here. But we would like to know, like, at what rate the car's approaching. So when car B moves, car A moves, the one that can connect these two are this Z. So it's actually, we can say, the rate that when car A is moving, car B is moving, is the change in Z. So this is actually our goal. Okay? Our goal. So our goal is to find dz dt. Because when z is decreasing, or when A is moving, B is moving, z is decreasing, right? Let me write here just to make sure that we are understand. So when A move, B move, z is decreasing. Okay, now when let me write here. So when x is 0.3, y is 0.4, and z will be 0.5. Okay, so all the rate we have done, so 50 and 60, that is A and B, the rate. So we can take this into our equations. And now let me write in terms of negative. So I will write dx dt in negative form. This is negative 50. This is negative 60. So this will be 0.3 multiplied with negative 50 plus 0.4 negative 60. So we get dz dt. Take some time to calculate. This will be 3,9, and then multiplied by 2 will be 78, right? 78. This will be negative 78 miles per hour. But I will say that I'm using this negative because I define the negative as decreasing. If you state the first dx dt and dy dt as a positive, this will be positive. But the meaning the same. It means that it is the rate at 78 miles per hour. Okay? So it doesn't really have different conclusion. Okay? So positive, negative, it doesn't really matter. Okay? It doesn't really matter as long as you know the consistency and the conclusion of your results. Okay? I'm writing negative because I want to make sure that all the decreasing part is the negative. Okay? So for example, if we take it positive, let's say this is become positive, this is positive, the answer will be positive 78. And it's still correct. It's still correct. It's still the value of the rate when the car is approaching. Okay. But I have some feedback questions. Yeah, class finished early, but I have feedback questions. Okay, so are you ready? Let me check. Okay. Now I will set this as a small quiz, like you can do it on your own, but it has timer. Okay. So let's start. Okay, that is the or I think maybe QR code better, faster for you to track the picture.